Hello, this time I will talk about acids and bases. We are going to break this acids and bases chapter into two chapters. Chapter 16. On this chapter, we'll cover general aspects and behaviors and properties of acids and bases. And then in the next chapter, chapter 17, we will cover the acid-base equilibria, where we'll discuss the concepts like buffer solutions, titrations, equilibria of acid-base, weak acids and weak bases. That's how we are going to manage this topic, acids and bases. So let's start with this one. I'm trying to start with a phrase to think about it. 10 lessons from Einstein. And I think we are on this one. We are up to here. 3, focus on the present. Supposedly, allegedly, he said this. I cannot confirm that. Any man who can drive safely while kissing a pretty girl is simply not giving the kiss the attention it deserves. Leave you there for your thinking about focus and present from Einstein's point of view. We'll start our acids and bases chapter with some general concepts, a little bit of history. Let's start with initial knowledge of the existence of these substances. In around Middle Ages, alchemists already had the perception of existence of some substances that have special behavior, possibly due to the presence of what we call now the H+ ions and the OH- ions. But it was around by the end of 18th century, the Lavoisier let me write it here. We're talking about end of 18th century. And he mentioned, or he suspected, that some substances containing oxygen have a special behavior, and he was talking about acids. Nowadays, we know that's not totally true. Not all acids contains oxygen. For example, HCl. aqueous. Later, on the same century, a German, that was about 1838, Liebig. He mentioned that acids contains hydrogen that can be replaced by metals, which is true. Some acids containing hydrogen can be replaced for more active behavior like metals. In about the same century, 1880s, that this is actually 19th century, was Arrhenius on Oswald. On Arrhenius started to give a definition of acids and bases, or acid-base theory. I'm not going to spend a lot of time on this definition. This was the classic old definition. He defines acids as substance giving H plus ions, and bases as substances giving OH minus ions in aqueous solution. I'm not going even to write it because we don't use the concept and there's no need to waste a lot of time on that definition. We're going to focus more on what Bronsted and Lowry defined. That was around 1923. Talking about Bronsted and Lowry. Danish and English. They came to the same idea or definition of acids, but they were working independently. They define an acid as a substance or a species having the tendency to lose a proton. And a base as a species having the tendency to gain a proton. So the two keywords here are to lose a proton, and that's for the acid, and to gain proton, that is for the base. We are going to stick with this definition for a while. This is the definition we commonly use to define acids and bases nowadays. So what is the meaning of this? Losing or gaining protons. What is a proton here? Because maybe you can relate this to the previous chapter. We're defining protons as a nuclear particle with positive charge. And the symbol we were using for the proton was 1, 1. One is the mass and one is the charge. Yeah. So are we talking about this proton? Well, somehow, yes. Let me explain. Basically, we're talking about a naked hydrogen. What is a naked hydrogen? Naked hydrogen is a hydrogen atom that loses one electron. So if we have let's do the electron distribution for hydrogen. Hydrogen, atomic mass 1, 0 charge on the atom. This is hydrogen. Atom, right, is neutral. That means the electron distribution for this is going to be 1 is 1. So it has 1 electron. And how many protons in the nucleus? We have 1 proton in the nucleus. For a protium isotope, that's the one we have here, protium, there's no neutrons. 0 neutrons on this atom. Number of neutrons, 0. 1 electron, 1 proton, and 0 neutrons. So in the nucleus, you can try to draw a diagram. There's 1 proton only, no neutrons. So that's the whole nucleus of the hydrogen atom. And 1 electron somewhere there in an orbital 1s1, right? Somewhere here. Statistically reported as being there, and the probability to find the electron there is 1 in the orbital 1s1. So 1 electron there. What is naked hydrogen? A naked hydrogen is a hydrogen atom that loses the electron. The atom loses the electron, it becomes in a different species called hydrogen ion, which is the nucleus and no electrons. And the symbol for that will be H plus, meaning it loses the electron there. What is left? Only one proton in the nucleus. That's why to this H plus ion, sometimes, or a lot of times, we call it just a proton, because that's what it is. One proton. There's nothing else in the nucleus. There's only one proton. No electrons. So that's why we sometimes call it naked hydrogen or hydrogen ion. So in the acid-base theory, when we talk about proton, we are just talking about H plus ion. Later on, we are going to see another version of that, because H plus, we can observe experimentally H plus ions only in a gas phase and under certain pressure conditions. So it's not easy to have H pluses around. In most of the times, when we talk about acids and bases, we are going to talk about aqueous solutions of these acids and bases, where they show that specific property. So H plus version, that version of proton will need to be adjusted, and I'll show you later. And that's why sometimes it's even better to talk about hydronium ion instead. So when we talk about aqueous solutions, in aqueous solutions, what we really have is H3O plus ions. All right, but we'll describe that later on. So, but that's the meaning of proton in this Bronsted-Lowry definition of acid. So if a species, and we talk about species and not just compounds, because these species can be ions, ionic species, or neutral species. They have the tendency to lose a proton. Whereas a base, according with Bronsted-Lowry, this species again could be molecular, could be ionic compounds, have the tendency to gain protons, H plus. All right, so let's see some of the properties of acids, and then we'll discuss some properties of bases. So in general, we say the acids are known for a interesting properties. So these chemical compounds, when in water solution, and this is important to remember, in water solution, acids have a sharp taste. Sometimes referred as sour. taste. Careful, we do not test chemicals. Do not taste chemicals. We know this because some substances that are edible, some acids that are present, those are weak acids in foods and fruits, shows that uh, particular charred taste, like for example, citric acid present on lemon, as an example, of orange, or even strawberries. That's because the presence of some weak organic acids, including citric acid. So as a safety precaution, remember, we do not taste chemicals in the lab. So also, those acids in aqueous solutions present another property, and we say that they are corrosive. They show a corrosive action on metals. That means they react with metals and they dissolve metals. Also, acids present another special property, something that is called effervescence. And that occurs when we add acid to a piece of chalk, and that produces the property, effervescence. And that is when you add a piece of chalk there. This is the chalk. And you add acid, it will start producing some bubbles and some fizzing sound there. And that is because it releases CO2 gas. That's a characteristic of acids. In other words, when you add acid to a carbonate, that reaction releases CO2 and water. Also, as a general property of acids, they turn some blue some vegetable dyes. So the turn, let me rewrite this here. The term some blue vegetable dyes, red. That's characteristic of acids. And you can test that if you have you can make some, for example, at home, you may have on your kitchen some cabbage, red cabbage. You can boil some cabbage pieces and extract the water, let it cool, and the cabbage extract will show you some color changes when you add acid. So usually you get up like a blue solution. That's the color of the cabbage juice. And you can add acids and you will see it turns to the red side. What about bases? Bases also in water solution have a bitter taste. Again, we know this because some foods, some edible substances can have that bitter taste. Also, bases have a caustic action, but this time on organic tissue. In other words, bases have the tendency to react and to dissolve organic tissue. That's why you had a feeling or a soppy feeling to the touch. Probably if on your kitchen you have the chance to handle baking soda, you put a little bit of baking soda on your fingers, add some water, and feel that touch. So you feel soppy or slippery between your fingers. That's a characteristic of bases. And that occurs because they have the tendency to dissolve the tissues. Our tissues have some fatty acids on the cells, so bases likes to react with those fatty acids in a process called saponification. And as a result, we get soap. Sometimes bases are referred as alkalis. So it's important that you recognize that word also. Alkalis. The alkalis refers to some bases that are made of hydroxides of metals, especially groups 1 of the periodic table. So we have NaOH, we have KOH, strong bases, and also hydroxides of the alkaline earth metals, for example, calcium hydroxide, magnesium hydroxide. These are strong bases. They have common names. Sodium hydroxide has been known since medieval age as caustic soda. What about KOH, potassium hydroxide? Has been known as caustic potash. Has been used for centuries ago. Our ancient cultures. And actually potassium was discovered on the caustic potash. Caustic soda, when you mix those two, is known as lye. So caustic potash contains potassium hydroxide, and potassium was extracted from here. And giving the name actually kalium. The symbol K comes from the original name that its origin comes from alkali, which is an Arab word from Arabic word alkali. Interesting, right? This one, calcium hydroxide in solution, is called commonly as lime water. And this one sometimes is referred as milk of magnesium. Interesting campsets that were known from long ago, like those ones, and they were used, aqueous solutions of this extracted from wood ashes and being used long ago to make soap through a saponification process. Anyway, sometimes you hear the concept application of this when you hear like alkaline soils. When the soil has a pH slightly above 7, it's what we call alkaline soils. Some plants like alkaline soils, like for example, cabbage. Some flowering plants also likes alkaline soils, and that's why some of them gives those blue colors or bluish colors. But most of the plants likes to have a slightly acidic pH. That means pH less than 7, 6.5, 6.8. And those type of soils we call acidic soils. And that is to, these alkaline soils have the pH due to the presence of some of these metal hydroxides. Another property or base of bases is that they turn some red vegetables dyes blue. So you have a red vegetable dye and you add a base, that color will turn blue in the presence of the base. So it's opposite behavior as compared to the acids. Bases are known also for the property or the ability to neutralize acids. So we have an acid and we add the base, we add a base to the acid, we have an acid-base neutralization. The base neutralizes the acid, or you can say the acid also neutralizes the base to form a salt and water. Remember, this needs to happen in an aqueous solution in general. All right, so knowing these basic properties will help us to recognize the general behavior of acids and bases. Let's jump to the chemistry part. We are going to discuss acid-base theory, including Bronsted, Lowry acids and bases, the acid-base properties of water, the pH scale. We are going to define the difference and find the difference between strong acids and strong bases, weak acids and weak bases. We are going to find Kas for the weak acid, Kbs for the weak bases. We are going to identify conjugate acid-base pairs. We will define the protic and polyprotic acids. And we are going to study the relationship between molecular structure and acid strength. Let's start with Bronsted acids and bases. This is a theoretical definitions of acids and bases. That's what we call the Bronsted-Lowry acid-base theory, or also Bronsted-Lowry acid-base model. Remember, this is a theoretical definition or interpretation of that behavior of acids and bases. So it's theory, it's just theory, or a model we use to describe these properties. And we can actually see this behavior experimentally. So for Bronsted-Lowry, acid is the substance that can donate a proton, and a base, or Bronsted base, is a substance that can accept a proton. Let's see this case. I will start with one strong acid. And that strong acid is hydrochloric acid. However, when we see the formula, it says aqueous. Let me go before that. What happened before we get here? So we have this compound, HCl, which is initially a gas. It's neutral, it's a neutral molecule that has one proton here. Also, we know this is a polar molecule. Hydrogen is in one corner of that molecule, and chloride, huge portion, huge atom compared to the relative size of hydrogen. It's more electronegative than hydrogen. That means it pulls most of the electrons towards this side of the molecule, leaving a little bit unprotected this corner of the molecule, forming a slightly positive dipole moment. And here, having a slightly negative dipole moment. Since this is more electronegative than hydrogen, these electrons, the sharing here pair of electrons, they are closer to the chlorine atom. So we can say this hydrogen-chlorine bond is relatively weak. In a gas phase, this is a neutral species and it's molecular. But when we bubble this gas into water, like that, then water, due to the high polarity property, especially oxygen in that water molecule, is able to take the hydrogen. So water molecule has two pairs of non-bonding electrons and is willing to accept the hydrogen. So those electrons takes the hydrogen there. To form this species that we call H3O+, and the name of this is hydronium ion. Or also we can call it a protonated water. It's a water molecule that has one extra proton. Remember, we're calling this a proton. Once the hydrogen gets out of that molecule, it goes naked. Just the proton, no electrons. Chlorine is keeping the electron, and that's shown here, Cl minus, because chlorine is keeping all the electrons. So we have, using the Lewis dot structure, and hydrogen has only one electron, and the electron is here. So chlorine keeps the electron, receives the negative charge. The naked hydrogen is adopted by the oxygen here, forming the hydrogen ion, or protonated water. So that's the process. According to Bronsted-Lowry, we call this, remember, we bubble this into water. And that transfer occurs only on water. So we have here the water. This species is in water, aqueous, plus Cl minus aqueous. So we need a solvent. And the universal solvent is water. We said water is the universal solvent for all acid-base reactions due to the special properties of water, the polarity of water, and the amphiprotic properties of water that we are going to discuss later. Here, we can classify, according to Bronsted-Lowry, the acid because it's donating a proton to water. To form the hydrogen ion and the Cl minus ion. And we call this the conjugated base of the acid. But also, we can say that this H3O plus is the conjugated acid in another reaction. Let's see this case. When we dissolve ammonia. Again, ammonia is a gas. It's a neutral molecular gas that we bubble into water to form the aqueous solution. To form NH3 aqueous. So what happens when the gas dissolves into water? Once it is aqueous. Let's see what's happening here. Let me go back to the first reaction. If we say this is an acid, because it has this property of giving off protons, what can we say about water? If this is behaving as acid in an acid-base reaction, therefore, we can classify water behaving with basic properties. So we define water as being base in that reaction. So the acid forms in an acid-base, according with acid-base definition, Bronsted-Lowry acid-base definition. Acids forms conjugated bases. And the base forms a conjugated acid. Let's do the same analysis, but this time using ammonia. So we already have the aqueous solution of ammonia dissolving the gas into water. So we collect the gas in water. And this is what we have now, the aqueous solution of that. That's the gas dissolved in water. This substance reacting with water will show basic properties because look what happens now. See on the other side, on the product, you will notice that ammonia has an extra hydrogen. So we have, this is the ammonia. Ammonia has one pair of non-bonding electrons. So we have the ammonia here. And notice that when ammonia accepts one proton, it becomes positively charged because of that proton that receives from water. So water, this is water, and this pair of electrons is strong enough to take that hydrogen, let's say, to steal the hydrogen from water. And what is left from this water molecule? This species keep this pair of electrons forming the hydroxide ion as a negative charge because it's keeping this pair of electrons. And ammonia gains that proton, gaining a positive charge. And this is what we call ammonium. ion. Notice that this base is classified as a base because it's able to produce hydroxide ions after accepting a proton. So bronze telluric acid explains very well the basic properties of ammonia, something that was not able to do if we were using Arrhenius definition. According with Arrhenius, a base are substances that gives off OH minus, but notice NH3 doesn't have OH minus to give off. That's why bronze telluric is even better than Arrhenius definition. Improves the definition. Now we can explain this basic behavior of ammonia through this reaction where we have OH minus as a product. Now let's analyze the acid-base conjugated pair. This is a base. If this is a non-base, therefore water here is working as an acid. This base forms a conjugated acid, and this acid forms a conjugate base. So these are common conjugate bases for different acids and bases. Let's check with more detail the process of formation of conjugate acids and bases. According with bronze telluric, the acid donates protons to the base. And as you can see from the previous slide, water is having double behavior. In some reactions behave as acid, let's say we have water plus water. What will happen at molecular level? We have pure water. Due to the nature and the structure of water molecules, water can take protons can accept protons to form hydrogen ions, or can give off the proton to form the hydroxide ion. So we have hydronium and hydroxide. And this is the hydroxide. And we call this species, hydrogen ion, as the most acidic. And this one, the hydroxide, as the most basic. So one of these is working as an acid and the other one is working as a base. So let's say this is the acid and this is the base. The acid gives off protons to the other one, and the base accepts protons on this one. As a result, we have a conjugated acid of the base and conjugate base of the acid. So we have there the acid-base pair. So the acid forms a conjugate base and the base forms a conjugate acid. And when water behaves as acid and base, we say water shows amphoteric properties. Here we can see that property. When we add hydrogen chloride to water to form the acid, hydrochloric acid, the water is behaving as a base. Because here, this is a very weak acid, and this is a very weak base, forming a strong acid and a strong base, the most basic and the most acidic. They comes from a very weak acid and very weak base. So this acid is stronger than this base, gives off that proton to water, and forming the conjugate acid, which is the hydrogen ion, and the conjugate base, which is the chloride ion. For the case of ammonia, ammonia is a weak base that can accept a proton from water. Therefore, water is behaving as acid due to the amphoteric properties of water. So the base gains proton to form the conjugated acid. And the acid loses a proton to form the conjugated base. Here, it is important to observe this other behavior. Ammonia is considered to be a weak base. And water is also a weak acid. This weak base forms a conjugated acid, but this conjugated acid is strong. Conversely, this weak acid forms a conjugated base. What did we say about this OH minus in terms of strength? We say this is the most basic species, so it's very strong. Did you notice any interesting pattern here? that when we're talking about acid-base pairs or acid-base conjugate pairs, the weak forms strong. The weak base forms strong conjugate acid. The weak acid forms a strong conjugate base. Keep that in mind, because we are going to need that analysis later on. Also, notice that we have an equilibrium here in this reaction. In acid-base reaction, you not always will see this equilibrium situation. That means if this is a weak reaction forming strong and strong products, what would you say about the position of the equilibrium? We can say that these two, once they are formed and since they are strong, will react each other right away, shifting the equilibrium to the left. So at the equilibrium position, mostly you will have unreacted base. And that's part of the definition of a weak base. We classify ammonia as a weak base due to that reason. Let's do the same reasoning on the previous one. Hydrochloric acid is now, or is being classified as strong acid. Remember, water is a weak base. This strong acid forms a conjugate base. What would you say about that? This is a very weak conjugate base because it comes from a strong acid. It's a pattern, right? Keep that in mind. Now, what would you say about the weak base? The weak base forms a conjugate acid. What would you say about the nature of this conjugate acid in terms of strength? This comes from a weak, so the conjugate is strong. And we said that before, because remember H3O plus, the hydrogen ion, is the most acidic species in water. So it's very interesting pattern here. Also, let's talk about the equilibrium. This is a strong acid giving all its protons to water to form the strong hydrogen ion. So what would you say about the position of the equilibrium? So this is very strong and is willing to give off all the protons. Remember, it's acid because it's giving off protons to the base. So the base gains protons and this is going to lose these protons, all of them, because it's strong. Shifting mainly the reaction to the right. So this is basically a one direction reaction. with very small equilibrium constant, very, very small, because the reaction shifts mostly and completely to the right, to completion, due to the nature of the strong acid, hydrochloric acid. So let's practice. We have some examples here. Let's find the conjugate acids and bases for some species. Notice that conjugate acids or bases can be neutral, can be molecular, or can be ionic forms. The key is to find who's accepting protons and who's losing protons. So the difference between an acid and its conjugate base is just one proton. Similar happened between the base and its conjugate acid. For instance, we have HNO3 plus water. So we are going to find the conjugate base of HNO3. Let's do the whole analysis so you can apply the analysis to solve the rest. These reactions, remember, acid-base reaction, all of them will be aqueous. Aqueous solutions. So don't forget to write that down. Has to be dissolved in water in order to present the behavior. So that means we add water. And let's see what happens. So the question is, find the conjugate base of HNO3. If they're saying find the conjugate base of this, that means this is what? Acid. If this is acid, because that's what it's saying here, right? The conjugate base of this. So who has conjugate base? Who forms conjugate base? Only acids. Who forms conjugate acid? Only a base. So this has to be an acid. If we are defining this species as an acid, therefore water must act as a base. Because this acid is going to donate the proton to the base, which is water, neutral. As a result, we know that this base, once accepts the proton, forms H3O plus, the hydrogen ion, forming here the acid-base conjugate pair. So this is the base, and this is the conjugate acid. And this is the acid. It's going to form the conjugate base, which is what? If this loses one proton, because gave it to base, so we have NO3 minus. Remember, the hydrogen goes naked, only the proton, and leaves behind its electron, and that's why NO3 gains one negative charge, and this has to be aqueous. Everything has to be aqueous in order to happen. And this is what we call the conjugate base. And that's the solution to the question. So the acid forms a conjugate base. I'll go a little bit further to classify as strong and weak. We classify HNO3 as strong. Strong acid. Therefore, it gives off a weak conjugate base. And we classify this as a weak base giving off a strong conjugate acid. This strong weak classification is really important. So I recommend every time you do this analysis, also do the strong weak analysis for every species. Notice that in our cases, most of the time, the conjugate bases have negative charge. And that makes them a good, sometimes good basis because they can accept a proton. But this species here is too weak. And the purpose basically here is to neutralize the total charge on the system. Because this species is not changing the pH of the solution. It's too weak to react with water. We are going to focus more on the strong piece of the conjugated acid or base. I'm going to do one more. One more example. Let's do this one. So we have HCO3 minus ion. Again, remember, has to be aqueous. So you need to write that down. Reacting with something here to form a conjugated acid and a conjugated base. Usually the notation, as you can see the notation I using, we write the acids first, then the base the next in the reactives, but it doesn't matter. You can put it base first, acid base. It's just I get used to put acids first and bases later, but that's actually a tendency in chemistry to write it that way. It's like a kind of notation. Same thing here, you write the conjugate. We know here we're going to have a conjugate acid. Here we're going to have the conjugate base. And here, this has to be opposite behavior, acid base, behavior as this. So this is the basic setup for you to solve these acid base pairs, at least to figure what is to identify each species. So let's read the question. The question gives you a lot of information. For example, it says, let's read the question carefully. Find the conjugate acid of HCO3 minus. We need to find the conjugate acid of that. That means that has to be a base. Because bases gives off of or forms conjugated acid. If this is a base, that means the base is donating a proton. So that base is going to lose that proton. To whom? The base is going to donate, because according to Bronsted-Lowry, bases are donates protons. So it's going to donate this. To whom? To an acid, right? Because acids are proton acceptors. To whom? Water. Because we are working on water in a water solution. This is pure water, liquid. So the base forms a conjugate acid. What is that conjugate acid? That's going to be so here the base, which is a proton acceptor, is going to accept the proton from the acid. Remember, the acids are proton, donates protons, and bases accepts protons. So the exchange goes from here to here. And what is the conjugated acid? Once the base accepts the proton from the acid, it's going to accept one more proton, right? Because it's a base, it's a proton acceptor. I think I was saying the opposite previously. So base is a proton acceptor according with Bronsted-Lowry. So it's going to accept one more proton. It's going to be H2, CO3, and the new, once it gains one more proton, it cancels out that negative charge. So we have a neutral species here. And this one that was donating a proton to the base becomes OH minus. Therefore, this acid forms a conjugated base. Let's analyze the strength. This is a strong base because it has a negative charge and is willing to accept right away a proton, forming the conjugated acid. Therefore, this conjugated acid is a weak acid. Water is always weak acid or weak base. But they forms conjugate strong base, and strong conjugate base. Very strong, OH minus. It has a negative charge and is willing to accept a proton right away. That makes it a very strong base. So this is the analysis you do to find the acid-base pairs. So on this reaction, on every reaction, you find two pairs, two acid-base pairs, or two Bronsted-Lowry acid-base pairs. HCO3 minus and H2CO3 pair. This being the strong base and this being the weak acid, conjugate acid. And another pair is H2O and OH minus, where water is the weak acid and the OH minus hydroxide ion is the strong conjugate base. Use this same strategy to find the conjugate acid on B and the conjugate base on C of this exercise. Now let's analyze the acid-base properties of water. We mentioned that water has a double behavior as an acid or base, and that property is called amphoteric. As we described before, in pure water, water self-ionizes. And that's called, the reaction is called auto-ionization of water. And sometimes it's written this way. This is a shortcut representation of the auto-ionization of water, where water, pure water, liquid, breaks down into H plus and OH minus. Usually I don't use this expression of auto-ionization of water. I prefer to use the complete ionization process for auto-ionization, because this really doesn't represent what's happening at molecular level. Remember, this species H plus doesn't exist. It exists only on a gaseous phase. It can be observed only on a gas phase and at low pressures. In aqueous solutions, we don't see this, doesn't exist. We can say that. What exists is the protonated water. That's why I prefer to write H2 liquid plus H2O liquid in equilibrium with H3O plus OH minus, aqueous and aqueous. We have the hydronium ion here, and we have the hydroxide ion, as I mentioned it before. So sometimes for simplicity, to simplify, we represent it this way. I prefer to use this way. So be familiar with both ways. This shows more realistic situation at molecular level, and this is just simplification of that. Since remember, in an equilibrium process, when we write the equilibrium constant, K sub C, for this process, we'll find concentration of H3 plus times concentration of OH minus over concentration of what? We can say concentration of water, but remember here is pure water, and we said that pure liquids and solids are not included into that expression. So we ended up writing the equilibrium constant as concentration of H3O plus times concentration of OH minus. And this is what we know as Kw. It's better known as the Kw for the auto-ionization of water. And that's what we have here. And that has been measured experimentally at 25 degrees Celsius. The Kw is 1.0 times 10 to the negative 14. That's for pure water at 25 degrees Celsius. Remember, the equilibrium constants are temperature dependent. If that is true, means that at 25 degrees Celsius for pure water, concentration of hydrogen ions equals concentration of OH minus, which is what? 1.0 times 10 to the negative 7. All right, because when we plug this number into here, 1.0 times 10 to the negative 7 molar times 1.0 times 10 to the negative 7 equals 1.0 times 10 to the negative 14 at 25 degrees Celsius. And these are constants for pure water. Very important constant, the Kw of water, which is the constant dissociation of water or constant auto-ionization of water. Very important value to take into account. It will help us to solve pH problems. So from there, for any acid-base process, what we have is a balance of ions. For any acid or base reaction, that's what we have. A balance between H3O plus and OH minus. On pure water, we just learned that these two concentrations are the same. Remember, the H3O plus sometimes is written as just H plus. H3O plus, the hydrogen ion, sometimes is written as H plus aqueous, and this is also always aqueous, right? This is a shortcut way to write it, and this is the actual species that we can find in the aqueous solution. So be aware of these two forms to represent the same thing. This is the hydrogen ion, and this is what we call the proton. This is the protonated water, which is basically the proton plus water, right? This is neutral. So these two makes that one. And this is what actually exists in the water, in the aqueous solution. So you can have solutions where the concentration of H3O plus equals concentration of OH minus, and we say the solution is neutral. It's well balanced, the two concentrations. Remember, they cancel out. The that cancels out the charges to form water. What do you get here from here? The opposite, the reverse of the previous reaction, right? So you have H3O plus aqueous plus OH minus aqueous, and you get what? Water. It's liquid. Reacting with another water molecule, liquid. So the opposite. So it forms an equilibrium there. Any acid giving off protons and any base accepting protons can change these levels of concentration here. So we have here like a it's well balanced. Let's say, let's put on a fulcrum here. Let's put the balance here, concentration of H plus. If we add acid, the acid will increase the concentration of H3 plus, making the solution acidic. So this goes up and this goes down. In an acidic solution, concentration of H plus goes up because of the presence of the acid you are adding, and this concentration goes down. Remember, Kw for water equals concentration of H3O plus times concentration of OH minus, and that is a constant number, which is 1.0 times 10 to the negative 14. No units. So this remains constant for pure water in a neutral solution. And it's neutral because these two amounts are the same. On pure water, we just learned this is, the concentration of this is 1.0 times 10 to the negative 7. And this is 1.0 times 10 to the negative 7. When you add acid to that solution, to that pure water, what's going to happen? This concentration must go up, and in order to keep this constant, this number needs to go down proportionally. Same thing happens here. When we add a base to water, the base gives off protons forming hydroxide ions, and this concentration goes up. So for a base, when we add base to this one goes up, and in order to keep the constant, this number needs to go down. So it's always a balance between these two. An acid-base reaction is that balance between these two concentrations. One going up for acids and the other one going down. So even in an acidic solution, you have some concentration of OH minus. It's just that it forms that proportion there. For a basic solution, so let's say this will represent how this concentration is changing. This one goes up, and this one goes down. Look, at the same proportion. For acidic. For a basic, we have this. This goes up, this concentration on the expression goes up, and this needs to go down by the same proportion. In order to keep this number constant. This is called Kw, water dissociation constant. All right, so that's how we analyze, we use Kw. Let's do an application of that. The concentration of hydrogen ions in the stomach acid is 0.10 molar. Calculate the concentration of hydroxide ions in the stomach acid at 25 degrees Celsius. Usually they specify the temperature, so we can use the Kw constant. If different temperature is given, we need to make corrections to that. But most of the cases we are going to do it at 25 degrees Celsius, which is room temperature. That means Kw is going to be 1.0 times 10 to the negative 14. So in order to solve the problem, we just use the expression and value of Kw. Kw equals concentration of H3O plus times concentration of OH minus, which is 1.0 times 10 to the negative 14 at 25 degrees Celsius. We need to find the concentration of this. This is given, and this in the stomach, that concentration of hydrogen ions is due to the fact that the stomach cells, the inner lining produces hydrochloric acid. So hydrochloric acid in the stomach produces, I'm going to write it in a simple way, in the shortcut. You see, plus Cl minus, like this. The long way will be HCl aqueous plus water liquid to form H3O plus aqueous plus Cl minus. Aqueous. So we know this concentration happens to be 0.10 molar, which is 1.0 times 10 to the negative 1. We just need to solve for OH minus here. So concentration of OH minus equals 1.0 times 10 to the negative 14, which is Kw, right? Over concentration of H3O plus. We already know this. Just put that number over here and let's find what is the new concentration. And that's what you get. So you see 0.10 molar of hydrogen ions are present, but also very small amount of hydroxide is there. If we know the concentration of H plus in any solution, we can elaborate something that is called the pH scale. pH is defined, it's a mathematical representation of that concentration. It's a way to simplify the way we write these concentrations of H plus or H3O plus and concentration of OH minus. And the pH is defined as the negative log base 10 of concentration of H3O plus. Or we are using the simplified way, it's just pH equals negative log of concentration of H plus. Remember, H3O plus is a better representation of the protons in the water. So in pure water, we can find what is the pH. Remember, previously we said that in pure water, the concentration of H plus equals concentration of OH minus. So let's find what is the concentration of H plus in pure water. And we just learned that in pure water, the concentration of H3O plus is 1.0 times 10 to the negative 7, which is the same concentration of OH minus. And we said previously that this is a neutral situation at 25 degrees Celsius. So if we plug this concentration into this equation, we will get the pH equals negative log of 1.0 times 10 to the negative 7 equals 7. So you can see the practical way to write or to express somehow the presence of these hydrogen ions in any aqueous solution. Something that is related directly to the concentration of H3 plus in that solution. That is a simpler way to write it. Because if we were to use concentrations, we will have to use scientific notation, huge numbers, sometimes very small numbers. But if we find the pH, it will be easier. It's a logarithmic scale. It's not proportional, it's a logarithmic scale to represent that concentration. It's important that you remember to add the negative in your calculation. So let me show you one example. Let me try to use my calculator here on the screen. I'll show you what happened here, and let's use scientific, let me see, yes, this one has log. Here, remember, this is base 10 log, and this is a natural log. The definition of pH is negative log of concentration of hydrogen ions. So let's say we have 1.0 exponent times 10 to the negative 7, right? So we have, what is my negative here? Lost it. No. I saw it. Okay, let me do again. Let me start again from scratch here. 1.0 times 10 to the negative 7. Common mistake when writing these numbers is this. Let me rewrite this number. This is the proper way to do it. I'm showing this because I know many times during the test, people fail because they don't know how to write these numbers in the calculator. Common mistake is this. Let's say 1.0, and people say times 10 exponent -7. Look, that's not correct. You see? All right, let me do it right again. 1.0 times 10 to the. That expression is simplified here, exponent. So you find your exponent function in your calculator. Sometimes this function is the first function, or sometimes the inverse, depending on your calculator. Sometimes the calculator doesn't show exponent, but shows something that says EE. So that exponent is simplification of when you say times 10 to the. So we hit that. I think I did already. I don't remember. Let me hit that. Okay, it's there. You see the E? That means this number times 10 to the exponent. And the only thing you need to do is to write the exponent, whether it's the positive or negative. And in my case, I had to write -7. In this case, I write negative first and then 7. And this depends also on the calculators. Some calculators allow you to write 7 and then you change the sign plus or minus. So know your calculator. So this is the proper way to write scientific notation on your calculator. This means 1.0 times 10 to the -7. And now we are going to take natural log of that. And let's see what happened. Here, sorry, not natural log, the base 10 log, which is this one. Look. What do you get? -7, right? But we don't want to use negative numbers. That's why the definition says negative log of concentration of H3+. So you can, the negative log is going to cancel this 7 and you will get always a positive number for pH. So don't forget that. And that's what we have here. You see, let's assume this negative is not here in the formula. What do you get here? Log of 1.0 times 10 to the -7 equals -7. But since we actually have the negative, you get +7. So it's very easy way to represent the concentration, the presence of hydrogen ions or hydroxide ions in the solution. Okay. So the pH, so we said the pH of the solution is 7. 7.00 usually 2 decimal places are good. You don't need to write more than 2 decimal places when representing the pH. Sometimes just 1 decimal place should be enough for more precise calculation when you are using more sophisticated digital pH meters, you can get up to decimal places. This is the scale of pH. Look, the relationship with concentration and the pH. Look the scale here. This is 10 to the negative 1, which is 0.1 molar, and the pH is 1. Look at the exponent and the pH number. This is 0.01, this is 10 to the negative 2. That's the concentration of H plus, and look at the pH, 2. Look at the exponent here, 1 times 10 to the negative 3, pH 3, and so on and so forth. 1 times 10 to the negative 12, pH 12. Remember, it's negative log of that concentration gives you 12. So we have now, as a result, a beautiful, nice scale of pH that goes from 1 to 14. Why? Because we just learned that in pure water, Kw, in pure water, Kw Kw equals concentration of H3O plus equals concentration of, sometimes I get so excited about this. Times concentration of OH minus equals 1.0 times 10 to the negative 14. Negative 14. Let's fix the mess there. Okay. Negative 14. So our scale goes from 1 to 14, the pH scale. And we classify here substances that have pH between 0 and 6.999, just before 7, they are acidic. Substances or solutions that has pH 7, that means concentration of H3O plus equals concentration of OH minus, and that is 1.0 times 10 to the negative 7 molar. This is OH. And we call this neutral. The pH is 7. And solutions containing concentrations or pH about 7, we call this basic. Some examples of pHs, so we have those as a reference. The normal stomach acid pH is 1.5. The lemon juice concentrated is 2.0. vinegar, which is about 5% solution of acetic acid, pH 3. Orange juice is 3.5. Saliva is between 6.4 and 6.9, slightly acidic. Blood, somewhere between 7.35 and 7.45, slightly basic. That's the pH of the blood serum. Tears, slightly alkaline or basic, 7.4. Milk of magnesia, we mentioned it before, which is a solution, aqueous solution of magnesium hydroxide, is 10.6, used as an antacid to neutralize the stomach acid, 10.7, that's the pH. The household ammonia, which is a diluted solution of ammonia, has pH 11.5, so it's very, very basic. The rainwater in clean air is 5.5, so it's acidic. If we have rainwater in a polluted air, like nearby industrial zones, industrial areas, the pH can go even down that, like 3.5, which is really bad for environment. It's very corrosive for environment and for living things. Changing the properties of micro ecosystems. All right. From the definition of pH, we can find something really important. So we can use this to solve problems. And applying one of the properties of logs. So let's remember pH equals negative, don't forget a negative log of concentration of H plus. To simplify, let's just leave it H plus or H3O plus. So from here, using the definition of properties of logs, and if we take anti-log on both sides, we find that concentration of H3O plus equals 10 to a negative pH. Very important, because if we know the pH of a solution, using this formula, we can find the concentration of H3O plus. So these two formulas, 1 and 2, and 2, this one comes from here. Number 2 is derivation of number 1. So these two formulas are really important to solve problems. Like, for example, let's do this problem here. Calculate the hydrogen ion concentration in a solution at 25 degrees Celsius. Notice that, yes, always 25 degrees Celsius, so we can use the Kw equals 1.0 times 10 to the negative 14. So let's calculate the concentration of hydrogen ion when we know the pH. So if pH is 4.76, yeah, you write it down. So you say pH equals 4.76. And what are we looking for? We're looking for concentration, which is 10 to the negative pH. So concentrate for the first case, 10 to the negative 4.76. Don't forget to write this negative here. It's very important. And so on and so forth. So those are the concentrations, right? So you do 10 to the negative 4.76. You plug down your calculator and you get 1.7 times 10 to the negative 5. 10 to the negative 11.95. So you can actually round that off to 1.1 times 10 to the negative 12. And so on and so forth. So you plug that in your calculator and you get the concentrations. So if you know the pH, you can find easily the concentration of the H3O plus. Also, it can be used to find the concentration of OH minus, because in general, if we say that definition of pH equals negative log of H3O plus, then we can use the same definition, logarithmic definition of POH. If this calculation gives you the hydrogen potential in the solution, so the POH will give you the hydroxide potential in the solution. So for POH equals negative log of concentration of OH minus, like that. In general, I'm going to write something here. The potential P of something, let's call X, equals negative log of X. That has applications because later on, if we have, like for example, I want to find the P of the equilibrium constant, that will be what? pK equals negative log of K. If we want to find the pKa, so that will be negative log of Ka. It wants to know the P, notice that P is lowercase, Kb, so it's going to be negative log of Kb. So in general, Px equals negative log of X. Using the same principle here. So it's a way to represent, to express large number using less figures in a logarithmic scale. Another important thing is that remember this is a logarithmic scale. Let me go back to the initial scale here. It's important that you remember and be aware of this, that the order of magnitudes here is not proportional because we're talking about a logarithmic scale. We are applying logs based then on these numbers to get the pH scale. So the pH scale is a logarithmic scale. So I have to be careful with the orders of magnitude. The concentration of H plus here Notice that the concentration of H plus, H3O plus here equals 10 to the negative 10. And for pH 11, the concentration of H3O plus is 10 to the negative 11. How big is this? This number compared to this? This is 10 times bigger. pH 11, the concentration of solution pH 11 is 10 times bigger than the concentration of OH3 plus in a solution pH 10, and so on and so forth. So it increases by factor of 10 every time. So it's a logarithmic scale. So be aware of that. So using the same concept applied to the POH, we find that POH equals negative log of concentration of OH minus. Therefore, concentration of OH minus equals 10 to the negative POH. If we apply that to the definition of KW, that we have before, we said that for pure water, at 25 degrees Celsius, at room temperature, 298 Kelvin, concentration of H3 plus times concentration of OH minus equals 1.0 times 10 to the negative 14, and this is what we call KW. We apply negative log on both sides. Since this is a multiplication, we can do that, and there's a property of logs that will be negative log of concentration of H3O plus negative log of concentration of OH minus. Remember, we are applying negative log on both terms, because you have negative times the whole expression equals negative log of 1.0 times 10 to the negative 14, and we know the negative log of that number is just 14. And what is negative log of H3O plus? Is pH. And what is negative log of OH minus? Is POH. Equals 14. Very important relationship for these acid-base solutions. pH plus POH equals 14. And that makes sense, because for a neutral, solution, the concentration of H3O plus is 10 to the negative 7. pH of that is 7. Plus POH, what is the concentration of neutral solution? Concentration of OH minus equals 1.0 times 10 to the negative 7. When we apply negative log of that, we get 7. 7 plus 7 equals 14. Very important relationship. pH plus POH equals 7. For example, if the pH of solution is, let's say you have a red wine, the pH usually 3.5. What is the pH of that wine? So the pH, so you say plus pOH equals 14. This is lowercase. So the pOH equals 14 minus 3.5, which is 10.5. From here, you can find the concentration of OH minus. Or you can find the concentration of H3 plus will be 10 to the negative 3.5. Or you can, for the pOH, you can find concentration of OH minus equals 10 to the negative 10 to the negative 10.5 negative. So this is the balance I was talking about before for the neutral solution. If this concentration of OH goes up, the other one goes down. If the pH goes up, the pOH goes down. Always pH plus pOH of the same solution equals 14. So we have a couple of equations that can help to understand relationships between concentrations and pH or pOH of a solution. This expression here, also you can use it to find concentrations. Because for example, if you know concentration of H3O plus, you can find concentration of OH minus on that. So concentration of OH minus equals 1.0 times 10 to negative 14 over concentration of H3O plus. So you see, you can use this equation, or you can use this equation here. Different ways to find concentrations of H3O plus, concentrations of OH minus, or finding pH or finding pOH on a solution. All right, I'm going to stop here. The next will be, I already did an example of this. We can do a couple more examples. You can try this yourself. I already showed you how to set it up. The next, I will talk about acid-base indicators. So I'm going to stop here and we continue on the next video.